There we go. All right, good. We're working. I want to open with this. Many reasons I would think you'd want to take this class seriously and try to pass, not the least of which is that you're paying for it. Another is just, it's never been offered here before, right? This is the first time they've ever offered this class. It may not be offered again. I don't know if it's going to be offered next semester or not. I don't know what the plan is. Nobody's talked to me. I may not be here next year. So if you're thinking like, well, I don't just want this bad grade sitting here that can never get replaced, now really is the time, okay? And I'm about it. If you want to retake a test, you want to whatever, I'm about it. I just need you to learn the stuff that I'm asking you to learn, okay? I will certainly work with you. Hence, stuff like this. You know that the next class we're going to have, or on October 1st, that's in 2 classes, right? You're going to have, you're going to be given just 2 lines. You're going to be right. Tell me all of this stuff, right? So we've done this a lot. We're going to do it again. And that quiz is literally just going to be, the stuff above this graph. Later on, maybe like the next week, you should expect everything else, which is just really understanding and interpreting this stuff, okay? So, this is the HR diagram, the Hertzsprung-Russell diagram. It tells me about stars. It relates several things. I've got these axes, right? What do I need to know about my y-axis?
Luminosity. Luminosity.
Luminosity, how bright it is. Right? It's true luminosity. Not how bright I see it from Earth, but how bright it really is in its place. When I draw an arrow, which way does the arrow go? Up or down? It goes up. Good. And what's on the y-axis here? Temperature. And which way does temperature run?
Right to left.
Right to left, right? And this is unique. You're not used to seeing graphs like this, right? It's inverted for temperature. Good. Okay. So it says here, show the stars. So where should I have stars? Yeah? Huh?
Everywhere.
Everywhere?
I mean,
I just want to go over here blindly and put
no,
dots, right? So, okay, so along this thing called the main sequence, right? So I've got this shape that kind of does something like this, right? So there's stars, that's good, but I also want to show like their mass. Mass is a measure of how much what? How much matter, how much stuff they have. The more matter, the larger they are, generally speaking, right? So, okay, along this main sequence, where will I find the biggest stars? Top left, right? So I'm going to draw these big, right? And down here, these will be the smallest, right? Something kind of medium in between. Something like that, right? That's not bad, okay? When you do this for real, you don't want all these dots. I'm just doing that to show, the general shape of the main sequence. Okay. All right. Very good. So we've got mass, we've got temperature, we've got luminosity. It's asking for stellar classifications. O goes where?
beginning.
Right here. O. Next.
B.
B.
A.
A.
F.
F.
G.
G.
K. M.
K. Yeah. Right? And that acronym that you always hear is O, be a fine girl, kiss me. If you can remember that, you can remember those in the right order. Good. So my biggest, brightest stars are O-class stars. My dimmest, smallest stars are M-class stars. The other thing I ask you that you got to know about this is color, right? So what color are these?
Blue.
These are blue. And over here?
Red.
Red. Good. Right in the middle?
Yellow.
Yellow. Good. And then either side I've got white and I've got orange, right? Good. So that covers my main sequence. But I got 2 classes of stars, the stars that are not on the main sequence that we haven't dealt with yet, right? So what are they?
Red giant.
We got giants. And there's more than just red giants. We haven't really talked about the giants a whole lot, but we will today. So over here I've got red giants, but there's also orange giants, and there's even blue giants, which are really weird. Okay, so I've got giants, and another thing is down here, right?
Dwarfs.
White horse.
These are the white dwarfs. That's probably not the right place. Let's go somewhere about here, right? They're white, so they... Okay. That about covers it, right? So there's all kinds of stuff I can deduce from this. I could ask questions about this. But if you really understand this, you're going to understand everything else that's on here, with just a couple exceptions. This is what you must know for that quiz. You get this right. If you got this, you'll have 100%. Okay? I'm not going to add anything. I'm not going to trick you up. It's going to be just that. It's literally, I'm going to cut and paste right off of this top part. You can do this. Let me make sure that I'm giving you proper things. Show the stars, represent the stellar classifications, color, temperature, mass, luminosity, label the axes, draw arrows to show the direction of the axis. This is it. Okay? You do this, you got 100%. I'll throw in one more thing. Okay? I will throw in, I guess it's kind of 3 more things. I would love for you to tell me that, hey, this is the main sequence. Okay? I'd love for you to tell me, not I'd love to, I'm going to tell you must tell me that these are giants. And you must tell me that these are white dwarfs. Okay? Most of us already know this. I'm going to ask you to label it. Okay? All right. And that's it. Okay? So do make sure that you know that. You got to tell me white dwarfs. You got to tell me giants. You got to tell me main sequence. Let's talk about the rest of this, because it's really interpretation and understanding of this. What is on the x-axis? Always temperature, right? And what's unusual about this x-axis? Runs right to left. Good. Everybody if you don't have this written down, I get these, okay? Make sure that with what we're saying right now that you have on yours. So, good. And what's on the y-axis?
Luminosity.
Luminosity. What is luminosity?
How bright it is. How bright it is.
How bright it is, right? It's a measure of energy also. That's why your bigger stars or your brighter stars, they have just flat out more energy. They burn brighter. Because they burn brighter and because they burn hotter, they also burn faster. The bigger, the more massive a star is, the quicker it burns out. So, again, it's not a question, it's not here, but which star is going to last the longest on the main sequence?
The red.
The red ones. And which one will last the least? Okay, I could ask the question another way. Which star on the main sequence will be the fast to enter the white dwarf stage? These guys, right? They're going to burn out the fastest, and so they'll enter this phase, and so then they'll enter this phase. Which one will be the slowest to enter a white dwarf stage? Well, actually, they'll never. Which one will be the slowest to enter a giant stage? It's going to be the red. Good. Okay. Okay. So those are just 3 different ways of really asking the same thing. Okay. Putting those pieces together. What are the individual points that are plotted on the graph? Stars. By the way, let me ask this from the test. We didn't do so good on certain parts of the test. What is a star?
The ball of gas.
If all you said was a big old ball of gas, I gave you full credit. I liked it better if you told me it's a big ball of gas that's doing, nuclear fusion or something like that. That's great. But I had a lot of people who did not tell me that a star was a ball of gas. And so that's tough at this point, right? We got to get that. Okay, we need to know that. Number 3. Most points along the graph appear along what shape? The main sequence. Okay? Main sequence. It's not quite a line, like a straight line, right? It's got a little curve to it. Yeah, okay. I would have given you credit. I'm in the credit-giving business, man. I'm looking to give points wherever I can. especially since I said shape, right? So a line would have been a good thing. All right. What's the name? Oh, I guess that would have been the right answer. It's a line. Okay, because the next one is, what's the name of this plot? The main sequence. Good. Where would I find red giants? Upper right, top right. Good. Where would you find very small, very hot, but not very bright stars? Kind of bottom towards the left. Good. Number 7. Along the main sequence, the hottest stars are found here. Where are the hottest stars? Top left. Right. This is temperature. So where do I find them? Got to be up here. Okay. Along the main sequence, the dimmest stars are found here. Bottom right. Right. So if this is luminosity, right, the brightest are going to be towards the top. The dimmest are going to be towards the bottom. That puts them down here. Right. Number 9, along the main sequence, the coolest stars are found where? Remember, this is temperature. Temperature increases as I go this way. So it decreases as I go this way. So my coolest ones are going to be over here. So they're these red ones, right? These are, I mean, y'all get this. This is just interpretation. This is really all the exact same stuff. It's just now we're going, not just draw this, but now do you understand what it's telling you? What information's on it? Okay? All right. Along the main sequence, the brightest stars are found here, upper left. Okay. Number 11, more interpretation. The hotter a star is, the blank it is in temperature. Well, that's redundant. How about that? Change number 11 to the brighter. The brighter a star is, the blank it is in temperature. Fix that. So you tell me. Take a look and interpret. Brightness is on my y-axis, right? So just look at where the brightest stars are. And what does that tell you about their temperature? The brighter it is, the hotter it is, right? Bright and hot. Okay, the cooler a star is, how about change number 11 to dimmer? I don't know what I was doing. The dimmer a star is, the blank it is in temperature. Cooler. Good. I'll give you all a minute on that. Number 11 was the brighter a star is, the hotter it is in temperature. Number 12, the dimmer a star is, the cooler it is in temperature. Now we're going to bring the color into it. The hotter a star is, the blank it is in color. Not brighter. Now this isn't asking luminosity, this is asking for color. The bluer it is. Good. And number 14, the cooler a star is, the redder it is, right? We move on that scale, on that color, Roji Bev towards red. That's great. 15 and 16 are really the same question, just asked 2 different ways. Number 15, put the letters of star classification in order from hottest to coolest. Well, that's what this is, right? Oh, be a fine girl, kiss me. That's from the hottest down to the coolest. Number 16 says put the letters for star classification in order from dimmest to brightest, right? So dimmest to brightest. So I've got to go backwards, right? M, K, G, F, A, B, O. M, K, G, F, A, B, O. Are we good at this moment? Anybody need anything repeated so far? Okay. Number 17, what's the classification of our sun? It's a G-class star. Our star is a perfectly average star. It has average temperature, average mass, average luminosity, average color, average everything. It is a G, right in the middle. All right. What color is our sun? Well, let's probably probably a little more yellow than orange, right? But somewhere in that vicinity.
So go with the orange/yellow.
I would give you credit. As long as I see yellow, we're cool. All right. Number 19, true or false? A star will change its location on the main sequence throughout its life. False. Wherever it is, it is. It gathers enough gas and begins fusion, and however big it is. Right? If it's little, then it's here. If it's big, then it's here. But they don't like start little and get bigger. They don't start bigger and get littler. They lose a little bit of mass, but not much. By the time they've lost enough mass that you think about them just getting smaller, they don't actually get bigger.
Right, so they're moving on sequence.
They move off of the main sequence. Okay, so it comes down to interpretation of the question. Okay, so the question again is true or false, a star will change its location on the main sequence. Now, if the question was, will it change its position on the HR diagram, that's a yes, they will. They'll move from the main sequence to the giant phase, to like the white dwarf phase, potentially to a neutron star or a black hole, depending on how massive they are after they're done with this. But they do not shift positions on here. However big they are, that's how big they are. When they run out of fuel, they'll go here. When they're done with this, they'll go somewhere else. Okay, all right. Number 20, where do stars first go when they leave the main sequence? Go to the giant phase, good. Number 21, these next couple go to our last class, the lecture that we had there, right? So there are probably as many, 2 words, stars as there are all other stars combined. Remember? Brown dwarfs, right? Like when I got home, last time we had class, my little kids asked me what we learned today. And I started telling them about brown dwarfs. And so then like you have to explain what a dwarf is. You just get asked 30 times at dinner about brown dwarfs. So anyway, brown dwarfs. What is a brown dwarf? This is they kept asking, what is a brown dwarf, Daddy? What is a brown dwarf?
The star that's not really started.
Yeah, and it never will be. Right? It's a big old ball of gas, just like a star. It got hot because of gravity, but it didn't get hot enough to start nuclear fusion. Okay? So it'll never, it's a star that, sometimes it's called a failed star. Just like it got so close that it didn't ever happen.
If we said failed star instead of brown dwarfs, would we get any credit?
I'd be about it. I told her, I'm in the point-giving business, man. I still really want brown dwarf, but I'm in the point-giving business. All right. Okay, where are we? 22. Theoretically, there are more blank stars than any other stellar objects. The answer is brown dwarf. Theoretically, there are more brown dwarfs than there are all the other stellar objects combined. I say theoretically because they're hard to find. They put off light in the infrared spectrum, and not that much of it to begin with, because they're not that hot. So they're dim, they're small, they're hard to find. Number 23, theoretic. I messed that up. Was that just 22 we just did?
Yeah.
Well, this theoretically, write it one down at the bottom, okay? Fill this in for me. Theoretically, I like that word apparently. The second most numerous stellar objects. Second most numerous stellar objects are learned this last infinity over it and
You
everything.
wanted to say what?
So at the very bottom, write your own question.
Oh.
Theoretically, the second most numerous stellar objects are?
No, red.
No,
Binary star.
binary stars. Binary stars, the stars that are existing in pairs, right? Over half of the stars that you see up in the night sky are pairs of stars, not just individual stars. If you had a telescope fine enough, you'd be able to see two stars orbiting about a central point. All right. Number 23, theoretically the third most numerous stars in the night sky are? Right here. And then the fourth, and the fifth, and the sixth, and the seventh.
So red stars.
Yeah. Red dwarfs, usually they're called. So the single most numerous thing out there, as far as a stellar object, is a brown dwarf. Second only to that are pairs of stars. Right? So again, we're not looking at even anything on this HR diagram. The most numerous things are not on here. I guess the individual stars in the binary system are on here, but brown dwarfs, then pairs of stars, and then there are a lot more small stars than there are big stars. There are not that many of these. There are tons of red ones. Okay, and we did a chart with that last time, and kind of remember I put like 93 dots over here, but up here I had like none, and here I had like 1, and then 2. And we graphed that, right? So that is the reality of it. All right. Where are we at? All right, number 24. The hottest and brightest stars shine blank because of, well, I shouldn't have done that. That's hard. When you get 3 blanks, it's hard to work with that. Hottest and brightest stars shine blank because they put off more blank light and less blank light than the other stars.
Shine dimmer because they put off.
Well, let's think about the hottest and brightest for a second. I won't do this to you on a quiz. I'm glad that we're going through this because I would mess you up if I did. That'd be hard to answer. So where are my hottest and brightest stars? Where are they? Yeah, they're here, right? Okay, so what color are they? Blue. Well, why are they blue?
Because they're hot.
Because they're hot, right? And because they're hot, I mean, literally, they put off more blue light than they do red light. If we were to, we've had this, I'll show you here. It's worth looking at. Let's see. Let's go to our Moodle page. Maybe. What happened? Okay. This right here. Notice the classification from A down to N, right? Oh, be a fine girl, kiss me, right? These at the top, those are the brightest, bluest stars. These down here are the dimmest, reddest stars. Those are the hottest stars. These are the coolest stars. Notice up at the top, the blue area is very bright. The red area is very dim. You go down to the bottom, and these red dwarfs, the blue or the red is very bright. The blue is very dim, right? So these are literally blue because they're putting off more blue light because of their temperature. And these are literally red because they put off more red light because of their temperature. Hot things burn bluer, or they produce more blue light. Cooler things appear redder because they put off more red light. You've experienced this if you've ever put any kind of metal in fire, right? The first color that you see, they begin to produce light because the individual atoms in there get excited, the electrons leave their orbitals and they go to higher orbitals, and then when they come back down, they release light. And so the first thing that you see is red. And then you'll see orange. And then if you leave it in there long enough and you can get it hot enough, it will produce blue light. And that's the exact same thing that's happening in a star. The temperature does reflect color because of that. So this question didn't come out so good on here. The hottest and brightest stars shine, I guess it probably should be blue because they put off more blue light and less red light than other stars. So in order there, it's blue, blue, red. They appear blue because they put out more blue than they do red. Doesn't mean they don't put out any red. They do, just not very much. It's not very bright. And the opposite is true down here at the bottom, number 25. The coolest and dimmest stars shine red because they put off more red light and less blue light. And again, you can see it on this. Lots of bright red, very little dim blue. Okay? And that's the deal. How does this class go so fast? All right. So what I want to do is I want to show you a video. It's not even that long over the HR diagram. And when that's done, actually, I guess I should ask, do you have any questions about any of this now? Anything you want clarified? Anything you want me to teach or reteach? Yes, sir.
Do we need to keep this?
Yeah, that's for you, man.
And when can we, because I know I didn't do that well on that last test. When
Yeah.
can we go back to retake that one?
I'm waiting on one person to come take it. But I'm about to give up on him because he hasn't come. I just need to give him back. Next class, I'm gonna give it back. Okay? And then we can schedule a retake.
Okay.
So if I have them, I'll give them to you now. Ask me at the end of class, and I'll hand them out. They're in my office. Okay? You can keep them. You need to figure out whatever we missed because the retake's going to be almost identical. I'll rephrase a couple things. If I ask it in this order, I'll ask it in that order or whatever. But it's going to be almost identical. I just want you to learn it. Okay? All right. Any other questions before we go on? Everybody's good? Okay. And I'm going to show you this.
A variety of stars with different brightness. As you look at this photo, you probably notice that there are a variety of stars with different brightnesses or magnitudes, and some are even of different color. Don't be fooled by this one. This happens to be a planet. But as you look up at the night sky, most stars do appear to either be blue or white, but some can be orange or red. And in this video, we will explore the relationships between color, brightness, and temperature using the HR diagram, which is one of the most important tools that an astronomer uses to classify stars.
Let
Welcome
me
to
go back
Learn
just
the
one
Sky.
second.
My name is Janine, and I'll be your guide as we explore the night that an astronomer uses.
So this is really useful to show you something we talked about. If they take a photo of just a swath of the sky, okay, and they figure out, okay, this is a blue giant, this is just a blue, main sequence, this is a red dwarf, this is whatever, and they sorted them by size and all those kinds of things, and then they graphed it. They put them where they're. Notice, man, there's a ton of these little red ones, and there's very few blue ones, and there's a lot more red giants than there are white giants, and boy, there's a lot more different sizes of white dwarfs than I expected, right? We're just trying to give general principles, but this shows relatively how many there are, right? And so when I ask you a question like, hey, what's the third most common or numerous stellar object? Well, yeah, there's a lot more of these red dwarfs than there are of these other things, right? A lot more. So this is just showing that.
Uses to classify stars. Welcome to Learn the Sky. My name is Janine, and I'll be your guide as we explore the night sky together, one constellation at a time. The HR diagram is a really important tool that astronomers use to show the relationship between star temperature and color against its brightness. And the development of this diagram was a major step towards understanding how a star evolves and changes over time.
And we'll be
The
learning that.
HR comes from Hertzsprung Russell, and Danish astronomer Enjar Hertzsprung and American astronomer Henry Russell developed this diagram in 1911. And this is what they came up with. When I teach my students about the HR diagram, I tell them that it's really easy to understand if you can interpret what each axis means. So let's start at the top. Here we have surface temperature of the star, and this is measured in Kelvin. So stars over here, at 3,000 degrees Kelvin, are much cooler and redder in color than stars over here. This is up to 25,000 degrees Kelvin, or it can actually get higher than that as well. Along this axis, this measures luminosity. So bring your attention right here. This is luminosity measured in suns. So if you come to the 1 and march yourself over here, you can find the sun. Absolute magnitude is just another descriptive way to measure brightness. And then at the bottom we have spectral type or spectral class. And the different letters represent different color and temperature ranges. And these can actually be broken down into like O1, O2, O3, O4 stars, describing how hot they are and their different colors. So here I listed what the spectral class is, what the color would be, and then what the temperatures would be as well. There is a mnemonic device that is used to help you remember what the spectral class is, and that is O, be a fine girl, kiss me, or you can use guy instead of girl, whatever helps you remember. But that mnemonic device can just help you remember what the spectral class is. Before we move on, I would like to tell you more about the sponsor for this video, Skillshare. Skillshare is an online learning community with a wide variety of tutorials. These are video-based quality lessons that can teach anything. Another important concept to understand about the HR diagram is what each of these categories mean in terms of stellar evolution. So first here, this long band that goes from the upper left all the way to the lower right, this is called the main sequence band. And this is where stars spend majority of their life. They are stable in terms of the pressure from fusion and gravity pulling everything to the center. So it's a balanced star. But over time, a star's position on this diagram will change. They begin as main sequence stars, they evolve into giants or maybe supergiants, and then eventually they fizzle away into white dwarfs. And to understand this, you need to understand the life cycle of a star. Now, eventually I will be doing a longer video on this process, but I can briefly go over it so you can understand how a star's position on the HR diagram will change. So all stars begin in molecular clouds with hydrogen and dust. And eventually something hits this molecular cloud, perhaps a shock wave from a distant supernova, and then protostars begin to form. And most stars, they form within clusters that are hidden inside inside a nebula. So once a certain temperature hits these, or the stars reach a particular temperature, the process of fusion begins. And then this is when stars become a main sequence star. The process of fusion is happening, stars are fusing hydrogen into helium. And we can have really massive stars that are typically blue in color, or you can have a low mass star like our sun or even a red dwarf star. Brown dwarf stars are essentially failed stars that never got hot enough to start the process of fusion. Over time, though, as a star starts to fuse up all its hydrogen and it starts to fuse heavier elements, the star enters its old age cycle. If it's a massive star, it'll turn into a supergiant star. If it's a low mass star like our sun, it'll turn into a red giant. So it grows in size. And then over time, you have eventually all the gases, there won't be enough mass to continue fusion, so it starts to fizzle away into these beautiful objects called planetary nebulas. And then it turns into a white dwarf. And a white dwarf is essentially a hot leftover core of a star. It's really, really hot. It burns. It's not too bright because it's just small. It's very small, but very hot. And eventually it fades into a black dwarf. But if you're a massive star, like a star like Betelgeuse or Rigel in Orion, what will happen is this star will become unstable, iron forms inside of it, and it turns into a supernova. And then depending upon its mass, it'll either turn into a black hole or a neutron star. So some of these objects that I'm circling right here, they aren't really seen on the HR diagram, but this pathway we can see some of these stars. So bouncing back to the HR diagram, I know that was like a really quick description of stellar evolution. There's a lot more to say on that topic, but that will be for a later video.
Football hurts. No pain, no gain. You gotta fight for it. What's Ted Cruz fought for? Himself. He wants to raise the retirement.
So here are these main sequence stars. Here we have these as giant, like blue giant stars, and then down here we call these red dwarf stars, and these are stars like our sun. And then what happens is as they start to run out of fuel, stars in this area will evolve into giant stars. So they're starting to grow in size. But stars in this arena, on this part of the main sequence band, will grow into supergiants. They'll get really, really big, and some of them will cool down, others will still stay relatively hot. But then as these red giants fade over time into planetary nebulae, they will eventually turn to white dwarfs. And you can see they're not as bright as the sun because they're lower in terms of luminosity, but they're still really, really hot. So I hope this helps you kind of understand the process of stellar evolution and how a star's position on this diagram will change over time. This is another version. I'm trying to show you as many versions as possible about the HR diagram. I like this one because it incorporates size here too, which is something you have to consider, because if you look over here, this is the main sequence band. And this is where stars spend a majority of their time on the HR diagram. And what this means is that they are balanced with the force of fusion along with the force of gravity. So everything in this band here is a stable star. But red stars just aren't small, they can also be very big, but they could still be the same color and temperature, which is really, really fascinating to me. Now, as a star gets older, depending upon the size that it is and upon its mass, it will change differently throughout its life. So here, we have F and G main sequence stars. These eventually turn into red giants, and then stars up here will turn into supergiant stars, which means that the location of fusion starts to change and the types of elements that are being fused changes as well. What's really fun about the HR diagram, at least in my classroom, is I had the chance to make it into a physical 3D model, and we did this by cutting apart styrofoam balls, and then we gave them different colors, we put glitter on them, and
You don't know how much I hate glitter. All right, we're done. Any questions? All right, let me pray for us. Father, thank you for this time that we've had and the opportunity to review and think about what we have and have not learned, things that we have learned. I just pray that you would help us have them really fixed in our minds, and the things that we see that we haven't, you grant us diligence to go after them. Helps just to have success. Pray this in Jesus' name. All right, John.